Decoding Algorithm Efficiency, Mastering Time and Space Complexity for Optimal Code Design. In today's data-driven world, the performance of code determines everything from application responsiveness to system scalability. Whether you're optimizing a sorting routine or designing a machine learning model, understanding how algorithms behave under varying input sizes is crucial. At its core, algorithm analysis focuses on quantifying resource consumption, primarily time and memory, to evaluate efficiency objectively. This knowledge empowers developers to make informed trade-offs when selecting or implementing solutions. Fundamental concepts in algorithm analysis. Before diving into specifics, it's vital to grasp foundational terminology. An algorithm's correctness ensures it produces accurate results, but even correct implementations can fail due to inefficiency. The three pillars of analysis include time complexity, space complexity, and practical performance considerations. While theoretical metrics guide decision-making, real-world factors like hardware capabilities also play significant roles. Time complexity measures execution speed relative to input size, often expressed using Big O notation. Space complexity quantifies memory requirements, distinguishing auxiliary storage from input size. Amortized analysis evaluates average case behavior over sequences of operations rather than individual steps. Understanding time complexity metrics. Time complexity categorizes algorithms based on their growth rates as inputs expand. Constant time operations remain unaffected by input size, making them ideal for optimization scenarios. Linear time complexity indicates direct proportionality between processing duration and input size. This is common in simple iteration patterns found in many fundamental algorithms. Quadratic time complexity emerges when nested loops operate on growing datasets. Such algorithms become impractical for large-scale problems unless optimized appropriately. Exponential time complexity represents worst-case scenarios where solution time doubles with each additional element. These are typically avoided in favor of polynomial alternatives whenever possible. Diving deeper into Big O notation. Big O notation abstracts away constants and lower-order terms to describe asymptotic behavior. This simplification enables meaningful comparisons between different approaches regardless of implementation specifics. While O, n, describes linear growth, O, log n, represents logarithmic scaling commonly seen in divide-and-conquer strategies. Understanding these distinctions helps identify optimal solutions for particular problem types. It's equally important to recognize that Big O doesn't reflect exact runtime measurements but rather identifies dominant factors affecting performance trends as input scales. Common Big O complexities. Compared O, 1 constant time operations remain unchanged irrespective of input size. Hash table lookups exemplify this behavior when keys map directly to stored locations. O, log and logarithmic complexity appears in binary search algorithms, reducing problem size by half at each step until reaching the desired value. O, n linear complexity occurs during single-loop iterations, such as summing array elements or traversing linked structures sequentially. O, n log and combines linear and logarithmic characteristics, typical of efficient sorting algorithms like merge sort and quicksort. Evaluating space complexity requirements. While time complexity receives much attention, space complexity is equally critical in determining program efficiency. Memory constraints can impact everything from mobile applications to embedded systems development. Auxiliary space refers to extra memory required beyond the input itself. This distinction matters significantly when evaluating recursive functions versus iterative counterparts. Some algorithms achieve better time complexity at the expense of increased memory usage, necessitating careful consideration based on available resources and problem constraints. For instance, selection sort operates in place with minimal auxiliary space, whereas merge sort requires additional memory proportional to the dataset size. Balancing time and space trade-offs. Optimizing algorithms often involves navigating trade-offs between time and space efficiencies. Choosing between different implementations depends heavily on context-specific requirements. Cache-friendly algorithms leverage spatial locality principles to minimize memory access delays, improving overall performance despite potentially higher theoretical complexity bounds. Data compression techniques demonstrate this balance well, trading off some decompression overhead for reduced storage demands across various computing environments. Profiling tools help quantify these trade-offs empirically, allowing developers to make evidence-based decisions rather than relying solely on theoretical estimates. Practical implications for software development. In web development, efficient algorithms prevent slow response times that could drive users away from applications. Back-end engineers particularly benefit from optimized database queries and caching mechanisms. Machine learning practitioners face unique challenges balancing training time against model accuracy. Feature engineering choices directly influence both computation costs and predictive power. Gaming industry professionals prioritize real-time performance, requiring meticulous optimization of physics engines and rendering pipelines to maintain smooth gameplay experiences. Cloud architects design distributed systems considering horizontal scaling possibilities while managing memory footprints across virtual machines efficiently. Advanced analytical techniques beyond basic Big O classification, advanced methods allow deeper insight into algorithm behavior. Amortization analysis reveals average case performance over operation sequences rather than isolated instances. Probabilistic analysis incorporates randomness into evaluation models, proving useful for randomized algorithms whose performance varies unpredictably with inputs. Recurrence relations formalize recursive algorithm analysis mathematically, enabling precise derivation of closed-form expressions describing time complexity. Taylor series expansions assist in approximating function behaviors around specific points, aiding in fine-grained performance tuning efforts. Case study: sorting algorithm comparison. Bubble sort demonstrates quadratic time complexity with O(n superscript 2), worst-case scenario, making it unsuitable for large datasets despite its simplicity. Merge sort consistently achieves O(n log n) time complexity through stable divide-and-conquer methodology, though it consumes additional memory for merging sorted segments. Quicksort's expected time complexity matches merge sorts, but its worst-case scenario degrades to O(n superscript 2), unless carefully implemented with random pivot selections. Insertion sort performs exceptionally well on nearly sorted arrays, showcasing how specific input properties can dramatically alter effective running times. Emerging trends in algorithm evaluation. With increasing emphasis on energy efficiency, researchers explore algorithms minimizing computational effort while maintaining acceptable precision levels. Green computing initiatives drive innovation in this area. Distributed computing frameworks introduce new dimensions to algorithm analysis, requiring consideration of network latency alongside traditional time/memory metrics. Quantum computing presents entirely novel paradigms challenging classical notions of complexity classes, pushing analysts toward fresh methodologies for evaluating quantum algorithms. AI-assisted optimization tools analyze vast parameter spaces automatically, identifying optimal configurations that would be impractical to discover manually. Tools and resources for effective analysis. Profiling tools like Prof and Valgrind provide empirical insights into actual program behavior, complementing theoretical predictions derived from algorithmic analysis. Visualization libraries enable graphical representation of complexity curves, helping developers understand how different algorithms scale with varying input sizes. Online platforms host interactive simulations demonstrating comparative performances visually, offering hands-on experience analyzing algorithmic behaviors. Academic papers frequently publish benchmark studies comparing state-of-the-art algorithms across diverse problem domains, serving as invaluable reference materials. Cultivating proficiency through practice. Mastering algorithm analysis requires deliberate practice solving varied problems systematically. Engaging with coding challenges reinforces conceptual understanding through concrete application. Participating in competitive programming contests sharpens analytical skills under press. Reviewing open-source projects' codebases offers opportunities to study real-world algorithm implementations, observing how theory translates into production-ready software. Collaborative debugging sessions enhance troubleshooting abilities, teaching how to diagnose performance bottlenecks effectively before deploying solutions. Conclusion: comprehensive understanding of algorithm analysis equips developers with the ability to craft high-performance software capable of handling modern computational demands efficiently. By mastering time and space complexity fundamentals while staying aware of emerging trends, programmers can continually refine their approach to building scalable, responsive applications across all technology stacks.